I think now we are already at 11 a.m. US Central Time. So 10 a.m. Sorry. Yeah. I think it's 11 US ET, right? So yeah. So let's get started. So my name is Qiao. I'm hosting this SIGCOMM Paper Reading Group since I think September or October in last year. So we take a short winter break and then the SIGCOMM paper deadline break. So after everyone has recovered from some meeting to SIGCOMM 25, we resume our meeting. So this will be our sixth meeting. So this week we will switch
recording in progress.
Okay, recording progress. Good. So this week we will switch to focus on large language model system. In particular, this week we will read a very interesting paper from last year's SIGCOMM called CacheGen. Essentially, this paper focuses on how to efficiently compress and streaming KV cache so that we can improve the network, the serving speed of large language model system. So as usual, today we will have a PhD student, which is not an author of this paper, to present. This week's presenter will be Jinghui Jiang, a PhD student at Xiamen University. And after Jinghui finish his presentation, and we are very happy to having invited Yuhan, the first author of this paper, to join us for a quick question Q&A and discussion. So if you have any questions during the discussion session, you can just speak, or if you think it's too noisy on your side, you can also type your questions or your comments in the chat channel, which I will be monitoring. So without further ado, so we will have Jinghui for the presentation. Jinghui, the floor is yours.
Thank you. I'm Jinghui Jiang, a second-year PhD student from Xiamen University. It's my great honor to present today's paper, CacheGen, KV cache compression and streaming for fast large language model serving. This paper was published in SIGCOMM 2024, and the first author is Yuhan, who is also today's special guest. This work was completed by the University of Chicago, Microsoft, and Stanford University. And now, let's begin. Large language models nowadays are equipped with context to answer questions not covered in training data. For example, in this ChatGPT session, the user first gives the large language model with Amazon's 2023 annual report. And then the user asks a question: what generates the most operating income for Amazon in 2023? Then the large language model is able to extract the information from the document, and it responds with the accurate answer. Amazon Web Service generates the most operating income. In this process, the user provides some history information to provide additional information to the LLM. We usually call the information, and in our example, the information is a document. We call it context. In this example, the Amazon 2023 annual report is a 92-page document. However, if we use context to provide additional information for inference in large language model, processing context can sometimes become very slow. In our example, we provide the large language model with Amazon's 2023 annual report, and then ask the question. After getting the input, the large language model first processes the context. In the environment of this paper, the large language model takes about 9 seconds to process the context. And then the model starts to process the user's query. Finally, the model can generate the answer for the user's query, and it returns to users that AWS is the most operating income in 2023. As we can see in this process, the large language model takes at least 9 seconds to process the context before the user gets the answer, which is a very slow process. So during such a long preview process, what happened in large language model? During such long preview phase, the large language model actually processes the context into a data format that the model can directly use. We call it KV cache. KV cache is a 3D tensor whose dimensions are layers, tokens, and channels. Tokens is the smallest unit processed by large language model, and the channel is the hidden state of the large language model. The size of KV cache is superlinear with the size of context. Still remember that the annual report is a 92 pages document. So the KV cache in this example is about 5 gigabit size. So such a long processing time seems necessary because large language model need to generate the KV cache for the long context. But luckily, the KV cache can sometimes be reused. Let's think about this. In our previous example, the user provided the 2023 annual report and a question to large language model. And then the model first processes the context and generates the KV cache. Then the model generates the answer based on this KV cache. The answer is AWS and the return is to the user. At the next moment, the user asks another question. What generates the most profit for Amazon in 2023? Then the model starts processing this query again. However, since the KV cache of the annual report is already cached in the memory, so it can just skip the processing of the context, and it can directly process the user's query. In this process, by reusing KV cache, large language model can complete the preview phase in less than 1 second, and the user is satisfied. However, most of the time things do not work out this way. In many cases, KV cache need to be transferred so that large language model can answer the user's query. It needs to be transferred from one GPU to another GPU. And here is why KV cache needs to be transferred. When the user inputs the annual report and the question to large language model, the model generates the KV cache for the context and generates the answer based on the KV cache. However, at the next moment, other users also start asking questions to large language model, and many other requests come in. At this time, the model calculates the context KV cache for different questions. Since the system memory is limited, so the model will clear the old KV cache from the memory. When the first user starts asking questions again, the KV cache of Amazon's annual report is no longer in the GPU. So this causes a large language model need to recompute the corresponding KV cache again. And similar problems also occurs on the CPU. Another possible situation where KV cache need to be transferred is the cross-server query. When the user asks the first question, the request is directly sent to server 1. So KV cache is also cached in server 1. But when the user asks the second question, the request is directly to server 2. In this case, if we want to reuse the KV cache, server 2 needs to load the KV cache of the annual report from server 1. Because some sometimes the link is not high bandwidth and the cache size is large. So sometimes sometimes loading KV cache from another server will cause network challenges. And so sometimes it is better to recalculate the KV cache than to transfer it from someone. So the goal of KV cache look like this. We assume that we have a network with 3 Gbps bandwidth in this system. If we calculate the KV cache of the annual report directly, then we need to spend about 9 seconds in preview context. This time is too long and the user are unlikely to be satisfied. So we try to reload the original KV cache and reuse this KV cache to shorten the time to preview context to satisfy user. However, because we have our networks is only 3 Gbps, so it takes about 14 seconds to load the original KV cache, which is slower than recalculated. So users are still not satisfied. To solve this problem, the goal of CacheGen is to compress this KV cache to make it less time to load. By sending compressed KV cache, the loading time can be significantly shortened. Although it requires a little decompression time, it is still faster than directly calculating and transmitting the original KV cache overall. So here is the overview of CacheGen. The CacheGen gets the original KV cache first, and then it compresses the KV cache to a bit stream and store it in the storage system. Now, when the large language model needs this KV cache to generate answer, it loads the KV cache from storage systems and use the GPU-based decompress to reload this KV cache and generate answer. The main difference between CacheGen and other work is that CacheGen transfer The main difference between CacheGen and other work is that CacheGen transfer bits instead of tensors. Previous work tried to compress KV cache into a tensor format. This is try to take advantage of the GPU's batch processing capabilities to quickly compress and decompress the KV cache. But for CacheGen, you choose to compress the KV cache into a bit stream because this is more natural for the network, and it can have a smaller result. And at the same time, in CacheGen, the two methods can work together to get their benefit at the same time. So how to compress the KV cache? To compress the KV cache, CacheGen have 3 key observations here. First is KV cache of nearby tokens are similar. So KV cache send the delta between tokens instead of the tokens themselves. And the second one is values grouped by channels and layers have better information gain. So KV cache CacheGen encode the KV cache by grouping the value according to the channel and the layer to obtain better encoding results. And the third one is that later layer endure more loss. So in CacheGen, it use higher precision compression for lower layers and lower precision compression to higher layers. For the first one observation, we know that the KV cache is a 3D tensor. So if we look closely at the tensor of the same layer, the vertical axis is channels and the horizontal axis is tensor. We can find that they seem to have some rules. Let me zoom in a little and we observe it. We can find that for close tokens, their values are similar, and for tokens far away, their values are different. The reason behind this phenomenon might come from the self-attention mechanism. Because of the value of each token is calculated based on the earlier value, so the value of each token will be closer to nearby tokens. This phenomenon in KV cache gives the author some inspiration. So what if the KV cache delta is compressed instead of the KV cache itself? For this layer of KV cache, CacheGen divides the KV cache into a series of groups, and each weighs about 20 tokens. In a group of tokens, CacheGen uses the first token as the anchor token, and the anchor token is used to calculate the delta of subsequent tokens. After doing this, the anchor token is still the original value, but other tokens are converted to the delta relative to the anchor token. After doing this for all groups, we can find that almost all values are close to 0. This means that the KV cache at this time has a smaller variance and is easier to compress. Before we start observation 2, we need to know something about arithmetic coding. The AC encoder takes the probability distribution and the symbol as input, and outputs a bit stream. All we need to know is that more skilled the input is, the smaller the output bit stream will be. For example, if we input has two symbols A and B, and there are 90% of the symbols are A and 10% are B, the encoding length is smaller than the encoding length of 50A and 50B. This means that when using the AC encoder, lower entropy gives better results than higher entropy. So the observation 2 is about how to obtain lower entropy. It is that values grouped by channels and layers have better information gain. The figure shows the difference between 4 different grouping methods when encoding KV cache. The horizontal axis of the figure is method, and the vertical axis is bit per element, or the entropy. The blue one is the method of using the AC encoder for encoding without any grouping, and the original one is grouping using tokens. Grouping using tokens means calculating the property of layers, token I, and channels. After doing this for each token I, we can find that it has a lower entropy than the blue one, and so as the yellow one and the green one. It can be clearly seen in the future that when using tokens for encoding, its entropy is much higher than when using channels and layers. And when using token for encoding, its entropy is even similar to no grouping. Group by channel and layer safe size. A possible explanation is that different channels or layers capture various features in the input. Some channels capture subject and object relationships, and others focus on adjectives. For the third observation, different layers have different tolerance to loss, and later layers endure more loss. That is, the earlier layers have lower tolerance, while the later layers have a higher tolerance to loss. As shown in this figure, this is measure of the tolerance of different layers loss. The horizontal axis is a grouping of the large language model layer, and the vertical axis is the accuracy of the LLM. The larger the value, the more accurately it is. All layers use the same loss. We can see that when using the same loading loss, small layers are more difficult to tolerate than large layers. It is because when shadow layers generate loss, the error will be sent to the later layer, causing errors in the subsequent layers as well. And when the later layer produces an error, because it is in the later layer, it will not affect more layers. So we use more aggressive quantization for later layers. In CacheGen, it compresses different layers with different precisions. For KV cache, CacheGen divided the KV cache into 3 parts. The first layer uses the highest precision, and the middle layer uses the medium precision, and the last layer uses the lowest precision. Because the layers with low loss tolerance have high precisions, and the layers with high loss tolerance have lower precisions, the overall precision loss is within an acceptance range. Another thing to note is that in CacheGen, for tokens in the same group, the encode token uses a higher precision, while the other tokens use a lower precision. This is because if the encode token has an error, it will directly affect the precision of entire group of tokens. And after the three observation, CacheGen have an additional design here. Because bandwidth changes can cause CacheGen to time out. For example, in this figure, at time 0, the bandwidth is 2 Gbps, and at time 2, it becomes very slow, and in time 4, it go back to 1 Gbps. For CacheGen, in time 0, it uses a high encoding level, so it will send a lot of data. But in time 2, the bandwidth is become lower, and the CacheGen still use high encoding level. And in time 4, it still use higher encoding level. So it completed the transfer in time 8 and out of SL. To deal with this problem, CacheGen use a dynamically adjusted compression level. Still at this bandwidth. At time 0, the CacheGen use high encoding level, and in time 2, finally the bandwidth go to a very slow level, so it switched to KV compute. And in time 4, finally the bandwidth go back to 1 Gbps, so it switched to low encoding level. And finally, you can complete the transfer between time 5 and time 6, so it satisfies the SL. In a word, the compression workflow is look like this. After CacheGen gets the original KV cache, the CacheGen first calculate the delta using delta encoding. This is convert the KV cache into a smaller variance and easier to compress. And then the CacheGen use smart AC encoder to convert KV cache into bit stream. Smart AC encoder use layers and channels to group KV cache to obtain smaller entropies and shorter bit streams. And then KV CacheGen uses layer-wise quantization for compress. Using different compression levels for different layers can achieve higher accuracy and more compact bit stream. And finally, KV cache get the bit stream. In CacheGen, it achieves the faster KV transmission speed by compressing CacheGen, but by compressing KV cache. But this also causes CacheGen to require additional decompress overhead. In order to not let decompression time slow down the system, CacheGen minimizes the decompression overhead. Because decompression AC on the CPU is slow, CacheGen writes a GPU-based decompression component using CUDA, and the pipeline loading KV cache with decompression. As shown in the figure, we can see the comparison between the prefill and the decompression stages. The vertical axis is the amount of computation. In the prefill stage, more than 200 teraflops per second of computation is required, while the amount of computation required for decompression is almost invisible. So when transferring KV cache, the decompression overhead may not be something that needs to be paid too much attention. In evaluation, this presentation may use the long chat dataset to demonstrate the accuracy of CacheGen. And there are two metrics to measure CacheGen performance. The first one is the size of KV cache. A smaller KV cache can complete the transfer faster and save the storage space on the storage devices. And the third one is TTFT, or time to first token. It is used to measure total prefill delay. The smaller the TTFT is, the less time the user has to wait. And we use the network bandwidth is 3 Gbps. The first comparison is about whether CacheGen
or type in the channel. We can do either way. But I think the first, I guess, let me break the ice for with a question. So basically, my understanding, I didn't work on this area per se, but my understanding is about CacheGen is actually you compress the cache and using some certain I think using certain encoding methods are very similar to a video streaming encoding. Is that my understanding correct? Like, if so, what would be the key difference between? Of course, the scenario will be different, but what are there other differences?
Yeah, that's a very good question. So yeah, the compression in CacheGen is analogous to video compression, but there are some key difference. For example, like we use like LM specific characteristics. For example, like we use more aggressive quantization for later layers KV. And also like we group like the way we group the KV cache into by channel and by layer is like specific is specifically beneficial for KV caching LLMs, if that makes sense.
Yeah, that totally makes sense. So essentially, compared with a video or picture, I mean, KV cache has its own characteristics. That's what you mean, right? So, but essentially, we try to leverage domain knowledge or this domain specific characteristics that creates new opportunity for better compression results compared with just pick whatever compression algorithm that's already there for video streaming. If we directly applied it to KV cache, it may not give you the best result, right? Cool. Yeah, yeah. So what's the overhead like to do the compression? So Jinghui, if you could go back to the overview slides of CacheGen. I think basically you when you got the cache, you try to compress it and put it in the storage media. I think in the memory, and then when other a server or GPU try to fetch it to load it, you just transmit it, and then so what's the overhead of compress? Does it take a very long time or not?
So right now, like the compression is implemented on GPU. So the overhead is really small. Like it can be much like much faster than the prefill itself. Yeah.
I see. Cool. Yeah, I think that makes sense. So essentially, you try to by leveraging GPU, you can do this compression really fast, and then essentially you don't lose. Essentially, you don't have a very high. Don't incur a very high cost. Yeah, that makes sense to me. Yeah, that's great. And I guess I'm just keeping asking questions because I really enjoyed this paper, but I do have a couple of questions. So what happens if the KV cache is like a swapped or updated? Do you do like a compression like incrementally, or once the KV cache is swapped, you just try to compress the swapped part separately? Is there any constraint on that? Yeah.
So by swapped, do you mean like if like the cache, like some part of the cache is updated by some other prompts, for example?
Yes.
Yeah, so what we do like so first like the KV cache will only like be if you update the KV cache, it will only be appended to the previous KV cache. And what we do is like we compress every time when a new KV cache comes in, like when new KV cache and we compress the new appended part and then save that like concatenate that in with the previous one and then save that into storage device 2.
I see. So okay, I see. Yeah. So I guess it's because the so let me see if I understand correctly. So because if other contact is swapped in as a newer updated cache, because it really has it's not highly related or highly coupled with other parts. So you don't have to do things like incrementally together. You can just compress them separately. Is that, I don't know if I understand correctly or not.
Yeah. So whenever you update the KV cache, like it will not change the previous KV cache at all. So it will it will only append to the previous KV cache, and all things in the previous part will not change. That's a property in large language models. Yeah. So
I see. Okay, cool. Yeah, then that's really not a problem, because like it's not a this could happen in other system, but not for large language model system. Cool. So there's a question from Vincent in the channel. The question is, can CacheGen decompression and decode run on the AI phone or AI PC?
Yeah, we haven't tested that on any low power devices yet. We just run it on like the GPU that we do inference for LMs. Yeah, but like I think like practically you should be able to apply use that CUDA kernel on any device. Yeah.
I see. So Vincent, does that answer your question? Okay, yeah, I think Vincent is still muted, but I suppose so. Okay, yes, great, wonderful. So, Jinghui, you have any questions for Yuhan?
I have two questions.
Okay, go ahead.
The first one is about let me find it. The first one is as we can see, there is a big difference between prefill and decompression. And in the paper, you say the decompression is based on GPU, so it is fast. But is the prefill stage based on CPU? Or if we based on GPU too, what's the main reason of this difference?
Oh, sorry. Just want to understand a question. So are you asking like is the prefill part performed on CPU or the compression part? So sorry, I didn't hear quite clearly the question.
My question is the decompression part is based on GPU. It's based on GPU, so it's fast. And the prefill phase, if it is based on CPU, why not make a GPU component to do this? And if it is based on GPU, and what's the main reason of the difference between these two phases?
I see. Got the question. So, first, the prefill is definitely performed on GPU, and it's basically a part of the LM inference. So the reason why the T-flops, the computation is much larger than decompression is the prefill includes the most computation expensive part in LM inference, which includes the self-attention, and that part is known to be high computation because it's growing quadratic computation algorithm complexity. So but like for our decompression, we only use some beat operations such as moving beats, and that is the computation itself is much smaller than prefill phase. Yeah, does that answer?
Recording stopped.
Jinghui, does that answer your question?
I guess I understand. So in fact, in prefill, it is contain a time of calculate the KV cache, and in decompression time, it is just decompress the KV cache.
Yeah, so decompression is only like a like a very small like computation to make the B streams that we compress back to the tensor format. So that part is a small amount of computation.
Understand. Thank you. And the second question is about the KV cache stream adaptation. In time 2, the CacheGen switch to KV compute, and in time 4, the CacheGen switch to low encoding level, right? So when the CacheGen finish the transfer, we have two parts of the CacheGen. The first part is get from the storage devices, and the computing part is calculated by the server. So how to ensure that these two parts can combine with the whole KV cache?
Okay, so basically like any part in this timeline, they will like in the end they will be converted to a tensor. They will generate a tensor format, and then basically you just need to concatenate the tensor format, either like decompressed by the GPU or like computed by the GPU together to get the final KV cache. Yeah. So I don't know if that answers your question.
My concern is that at the time 2, I think it must be some group of tokens that are still be sent, but the bandwidth is now very, very, very slow. So if the group in time 2 is still sending, they be cut off. What will happen at this time?
I am not sure if I understand your question fully. But yeah, yeah, sorry, please go ahead.
My question is, at the time 2, when the bandwidth gets very, very slow, there must be some group of tokens are still sending. And the CacheGen switch to KV compute. Whether if it compute the group they're still sending.
Okay, like in CacheGen, we chunk the whole KV cache into many groups of tokens, and for example, if like at the timestamp 2, the bandwidth starts to drop, then like if it's still transferring like in the middle of the chunk, we will just abandon that chunk's transmission and starts recomputation from the beginning of that chunk, and then starts yeah, basically we won't like be transferring like that chunk. But we won't be finishing that the transmission for that chunk. Yeah.
I understand. Thank you.
Yeah, so question here. So do you mean like, sorry, just one short question on this figure. So do you mean like from the second like time step 2 to time step 4, like we only do the recomputation but not streaming the KV cache to the destination?
Yeah.
Is that what you mean? Okay,
Yeah.
got it. Thank you.
Right. So Fengzhen from Princeton has been raising her hand for a while. So Fengzhen, go ahead.
Thanks. Great talk. So it's following up Professor Xiang's question. I understand you kind of utilize some of the advantage of LLM. I wonder, like within one layer or one channel, have you tried some traditional compression methods, such as like the Hoffmann encoding? And how do these work? If not, like what are the specific challenges that like KB cache or tensors pose here? Yeah.
It's a very good question. So, we didn't specifically try Hoffmann encoding, but we tried something like gzip, to as original like floating point tensors. So the thing is, like the KB cache is not a sparse data. So like traditional compression methods such as gzip doesn't really work well on that case. Yeah, so that's why like we need some like some specific like methods like what CacheGen does to make it like more suitable for those compression methods such as AC.
Got it. Yeah, thank you. If I can ask another question, so you were
Oh, absolutely.
okay. So actually the in compression is streamed so that you can do compression and streaming, like sending at the same time. Is that the right way I understand it?
Yeah,
Like
so we have to like compress one chunk and then so actually in CacheGen we the compressions happen in offline phase. So like basically like we are thinking of like for example like one previous like prompt uses this KB cache and then like at the offline stage, we compress it and save it into storage device. So like when another request comes in querying the KB cache, we do decompression and streaming at the same time. Like yeah.
oh,
So
I see.
don't really do like compression and streaming. Yeah, it's not a on-demand like compression in CacheGen. Actually,
I see. So you don't have to get all chunks to decompress. You can, as fast as you receive one chunk, you can start decompress. Okay,
exactly.
that makes sense. Thank you.
Thank you.
Cool. So I see Hao from Jinghua has another question.
Hi, Yuhan. So I have a short question. So recently, like DeepSeek have released their I think it's native sparse attention. So it's kind of like they are doing compression and also trying to reduce the necessary attentions need to be computed during the inference. So in that sense, like might like reduce the sparsity of the tensor itself, of the attention itself. So that would make the compression become more difficult. And also because they are using this kind of native sparse attention, so their attention may not like contiguous as before. So because they are selecting some attentions, not using all attention. So is that also pose a challenge for like the KV cache compression, like streaming compression? So do you have any comments on that? Thank you.
Yeah, that's a very good question. So I think that those kind of like sparse attention is kind of similar to like the H2O compression. Like basically they drop some tokens in the middle of the KB cache. So I guess like CacheGen, those kind of KB cache compression methods should still work on those sparse attention, but like you may need to do some hand tuning of the compression methods to make the compression ratio as large as possible. So I think like short answer is like it should still work. The compression should still work, but may need some hand tuning. Yeah.
Okay, thank you for your answer. Yeah.
Yeah. So I see. Yan Nian Niu. Sorry, I don't know if I pronounce your name correctly. Yeah, go ahead.
Good morning, host, president, and author. Firstly, thank you for holding this online reading seminar. And I read this paper a few days ago, and I got a question. I noticed that in these slides, you provide an example that firstly the first user provide a contact the Amazon annual report to the first large language model, which is directed to server 1 and ask a question about that Amazon annual report, and then after some while, the second user also asks some relevant questions, which is directed to server 2, and then at this time that CacheGen need to transmit the KV cache, which is computed by the first server and stored at transfer this KV cache to the second server. So my question is how to match those KV cache which is stored on a remote server to the second second question from the second user.
Yeah. So like here, like the second question, we assume like they are this question also requires the Amazon's annual report to answer the question. So basically what we do is we do a string matching, and so first we have a key value store to save the hash of the Amazon's annual report in the remote server, and then like when the second question comes in querying the annual report, we compute the hash of the queried annual report, and then we find there is a match in server number 1 where we will fetch the like its KB, its corresponding KB to server number 2. Yeah.
Oh, okay. So if my understanding is correct, so firstly you did a hash computing about the context provided by the first user, and then for the second query question, first query from the second for the second query, you also do some hash computation and do some match action. Is that correct?
Yeah.
Okay, so it's like a exact match or a semantic match.
It's an exact match in
Okay. Thank you for your answer. I got that.
Okay, so we only have a few minutes left, but let me abuse my power as a host to ask Yuhan a couple of non-technical related questions. So this is a wonderful work, but so what motivates you to look into this problem? This is like Junchen just throw this question, say, I have this question, solve it, or you fund it by yourself, or like after reading a lot of papers, realize or do lots of experiments saying, hey, this is something nobody has looked into or nobody has good solution so far. So what motivates you to do this and came up with this idea to compress the KV cache?
So when we are we did this paper at the beginning of 2023, and at that time we were just doing some exploration in like the LM space, and then we find like the KV cache in LMs can speed up the inference a lot, and also like it can have a a very large size in size. So that's why like we think we were kind of like inventing the problem. Like they may like people may transfer the KV cache from remote from remote server, and then we start to think like maybe we should do compression on KV cache to make the streaming faster. Yeah, so at that time we are basically like inventing the problem, but luckily like we find like right now current in industry nowadays, like they are actually doing this kind of streaming of KV cache. Yeah.
Cool. So yeah, I remember that last year in Sydney, Junchen was giving a keynote at APNet. So I think basically it's centered around CacheGen. So I still remember he's very energetic and feels really excited about this topic in general. Yeah, I think yeah, I agree with him. This is a very exciting and lots of opportunities here. So during this work, like what is the most difficult things you have to work out? Like and what is like to make a breakthrough? Like what's your aha moment, I guess?
So I think the most difficult part is trying to think of this compression algorithm, like and the second hardest thing is how to make the compression or decompression overhead as little as possible. Yeah.
Okay, so is it like you try a lot, try different things, or like little by little, and at one day you found it, hey, this looks like a reasonable design, looks a good result, or is it like you get stuck there for a very long time, and someday, yeah, maybe when you are jogging, you suddenly realize, hey, I can do this. So what is like?
Yeah, I think yeah, we kind of explored a lot of technologies, but like we feel like doing quantization and arithmetic coding is like the I would say the most clean way like we found at that time to do compression. Yeah, we kind of got stuck for a while. Yeah, and then yeah, came up with this technique. Yeah.
Okay, cool. Yeah, that's very exciting. So what's next for CacheGen? I see you're working on lots of a couple of like open source large language model projects.
Yeah.
So is it like a continuation of CacheGen, or you are exploring something new?
Yeah, it's kind of like we want to make CacheGen into like a more like a production ready like
Makes sense.
Yeah, so that's why we have a new open source project called Production Stack under VOM, and in that we use like CacheGen's compression and all this kind of KV cache we use to make like the inference faster. Yeah, that's something I'm excited about right now. Yeah.
Cool. So have you tried out the effects of CacheGen on DeepSeek?
Not really. Yeah, like that's on our roadmap, like trying.
Okay.
Yeah.
Cool. Yeah, and just to give you a little bit like a preview, so we are currently trying to arrange a talk with Peking University in our next meeting at SIGCOMM Reading Group, because I don't know if you know Professor Tong Yang. He's a very productive in our community, and one of his students is working with a couple of other companies in China, try to make DeepSeek basically try to make the DeepSeek become more lightweight without sacrificing the accuracy. So I think they recently make some big breakthrough, and I talked to them this morning, and they say they are working on the technical report, and they're hoping to wrap it up maybe next week. So the week after next week, at the meeting, I invited them to give a talk about that. So hopefully they will find squeeze some time from their busy schedule. We'll see. No, but by reading the abstract and the news article, it seems like something very exciting. Yeah. Cool. So yeah. So if for everyone, if you're interested, yeah, then we can do that. Oh, so I think there's a immediate question from Anthony. Oh no, he's not with DeepSeek. I need to clarify. He's working on building on something like on top of this DeepSeek. So I can give you his name. Let me see. Yeah. Yang from Peking University, China. Yeah. And his student is Yuhan Wu. Let's see. Student at PKU. Right. Okay. So I think we are already like 5 minutes over. Let's thank Jinghui and Yuhan again for the wonderful presentation and discussion. Lots of questions, and I clarified lots of things. I now have at least myself had a very a much deeper understanding about this paper. Really very exciting. Yeah, congrats on Yuhan and Junchen. A wonderful work. Yeah.
Thanks for inviting.
Okay, cool. So with this, we will adjourn for now, and we will meet again 2 weeks later. All right. See you. Hope to see many of you in 2 weeks later. Okay. Thank you. Have a good day and good night. Bye.